Hi, I'm Paul Morin with the Energy Conservatory, and welcome to our webinar on Zone Pressure Diagnostics for optimal air sealing and insulation. A few housekeeping items. If you do not hear anything on your computer speaker system, you'll need to dial in and listen to the presentation over the phone. If you have questions for the presenter, please type your message in the question box at the right portion of the screen. If you have comments for the audience, please type your message in the chat box at the right-hand portion of your screen. Please be aware that your level of interest is being recorded and will affect your final BPI continuing education value. And basically what that means, if you're doing other things on your computer besides watching and listening to the webinar, it may affect your credit. The session slides will be made available on the Energy Conservatory website within a week. And the objectives today, we're going to talk about what is zone pressure diagnostics and why is air sealing important, when to take direct zone measurements, when to use advanced zone pressure diagnostics. We'll go into detail about that. Direct measurements are simply taking a pressure measurement into a zone. And advanced zone pressure diagnostics requires adding a hole or opening a door to that zone or from that zone to the outside to calculate how much leakage there is between the zones. And throughout the presentation, we'll be talking about how to take the best measurements. The zone pressure diagnostic tool has been used since 1990. It's my understanding that it was first developed when Jim Fitzgerald and Michael Blasnick were working on some row houses in Philadelphia, and they discovered if they measure the pressure in the attic with the house at 50 pascals, that the attic pressure number is proportional to the amount of leakage. So that's kind of what started it all, and it's been used quite a bit since 1990 to help diagnose problems. It's used to identify and measure series leaks. A simple series leak would be air leaking from a house to an attic, and then measuring from the attic to outside. And the amount of leaks through that series depends on the openings on both sides, both house to attic and attic to outside. And zone pressure diagnostics is used to identify those series leaks. A more complex series leak might be air leaking into a wall cavity, that's leaking into a drop soffit cavity, that's leaking into an attic space. And again, the leakage into and out of each of those spaces determines how much air is going to move through those. Basically, again, you need both a pressure difference and a hole in order to get air movement. So the amount of air is dependent on both of those issues. You'll always be depressurizing house to 50 pascals and then measuring the pressure to the zone, and to use zone pressure diagnostics. And the pressures are a ratio of leakage areas, and we'll go into that in some detail because this is a critical thing to understand about interpreting these zone pressure numbers. Why is air sealing important? First, we're going to talk about there's an air barrier or pressure boundary. Those are interchangeable terms. And we'll want to know where the air barrier is so we can determine where to air seal. And sometimes the air barrier isn't where we want it to be. So it's also about determining where the air barrier should be and determine and air seal at that location. So we have to define where the pressure boundary is and then air seal at that location. And we're going to want to know, do the pressure boundaries and the insulation boundaries line up currently, and where do we want them to be? The insulation boundary, thermal boundary are interchangeable terms, and we always want our pressure boundary and our insulation boundary to line up. And at the beginning, I'll show a case study that shows what can happen when we don't have these thermal boundaries and pressure boundaries properly aligned. Air is able to move through the insulation, and it makes the insulation much less effective. In order to have effective insulation, we need the pressure boundaries and the thermal boundaries to line up. And zone pressure diagnostics can aid us in determining if these pressure boundaries and thermal boundaries are lining up. We're also going to look at our zones of a poor air quality, such as garages or crawl spaces connected to the indoors. Typically, garages and crawl spaces are on the intake side of the house, where air is leaking into the house from these spaces. And if they are, we want to make sure that we get those sealed up. Is warm, moist air getting from a cold attic space, cold attic getting into a cold attic zone, warm, moist air from a house? On the exfiltration side, is air leaking from the house into a cold attic space, causing attic frost, attic condensation, and possibly durability issues? We'll look at that also. Those of us in cold climates that have the luxury of living in cold climates, we can see when we have problems with pressure boundaries and thermal boundaries not lining up properly, because we start seeing huge ice dams, long icicles, and water backing up into houses behind these ice dams. This example is one that Peter Burns and I went out to investigate before we worked with the Energy Conservatory near Lake Wobegon. You can see here they had to put a caution falling ice sign out because it was dangerous because of the length of the icicles and problems entailed in it. So you can see the workman is up there with the lift. This was as I recall, about a 40-unit condominium complex, and about 2/3 to 3/4 of them had water leaking in from these ice dam issues. So certainly huge problems. It's in areas of high snow levels and in cold temperatures. These were below zero temperatures when we went out and did this investigation. So the first step was knock all of the icicles off of the roof to prevent people from getting injured, and then snow blow off the snow. So now the water can't leak in if there's no snow on the roof. And next, jackhammer off the icicles and the remaining ice dams. The workman mentioned that in some locations, once he jackhammered through the ice and got to the water that was underneath the ice, water would spurt up like a geyser. So serious problems. And those of us in northern climates have the luxury of being able to visually see when those types of problems occur. And lots of parts of the country this year had that luxury too of having the extra snow, and we're able to see these, visually see these issues that are occurring. But oftentimes in parts of the country and most of the time of the year, you don't see those pressure boundary issues with a thermal boundary, pressure boundary aren't lining up. But there are ways that you can measure that. And that's where zone pressure diagnostics comes in. It gives you an idea if the pressure boundaries and thermal boundaries are lining up in the right location. Visible signs might be ice dams, uneven snow melt, attic moisture issues, and these are mostly cold climate issues, but certainly could be problems in higher temperature areas where you have high humidities. You start seeing not only attic moisture issues, but moisture issues in places you wouldn't suspect, or maybe in the whole house. Infrared with blower door also helps find if there's a lot of attic bypasses. In this case, in this example, we suspected a lot of attic bypasses because of the severity of the problem. So we did an infrared camera scan before the blower door test. We did the blower door test and then did the infrared camera scan with the blower door running, and we didn't find any bypasses, and that did not seem right. So we went up into the attic and found that the attic temperature was almost exactly the same as the temperature in the room, because our pressure boundary and our thermal boundary weren't lining up. There's so many attic bypasses and so little venting. There was some ridge venting, but not much low venting, so the cold air from the outside wasn't getting pulled in. The venting was essentially just venting out the warm air that was leaking into the attic and not drawing any outdoor air in from the low roof vents. So we left the attic hatch off, left the blower door running for a while. That cooled the attic down enough, put the attic hatch back in place, and were able to find the bypasses using the infrared camera. So what happened was the pressure boundary was the roof rather than the attic ceiling. And in cold climates, every once in a while we get 12 inches or more of insulation falling from the sky and accumulating on our roofs, and snow can actually be a pretty good insulator. So now that insulation was added to the roof overnight, our pressure boundary and thermal boundary are aligned, but they're not aligned in the right location. So the air is just bypassing the insulation on the ceiling, going up to the pressure boundary and the insulation on the roof, and warming up the attic spaces. So we've got two options when aligning our boundaries. If we add proper attic venting, we could, in this case, make that attic colder and reduce the amount of ice dams. Or we could seal the attic bypasses and make the attic colder. So you can come at it from two approaches. It's certainly best to seal the attic bypasses because you can run into other issues with adding attic venting alone. In this case, you can see there was about 18 inches of insulation, and that was pretty consistent of blown fiberglass insulation. One of the tenants was a realtor, and she was sure there wasn't enough insulation and more insulation would solve the problem. She added an additional 18 inches. She added 18 inches more insulation on top of the existing insulation. Now she's got 3 feet of insulation up there, and it made very little difference in the problem because the problem was not enough attic insulation. The problem was part of the problem was the huge amount of bypasses. As you can see here, there's a drop ceiling detail. In some of the units, they had just filled this up full of insulation and insulated over the top. In other cases, they had stapled cardboard over the top. Stapling the cardboard wasn't sealed. Helped a little bit, but you have to remember that this is a 2-story building with a basement, so a tall building with extreme cold, below zero temperatures. The stack pressures on a house like this are going to be 5 or 6 pascals in the wintertime. So even if you have cardboard stapled over the top of this, it's not enough. You're still going to get quite a bit of air leakage through a bypass of this size. Some of the other bypasses, there were lots of them. Drop soffit details. One other unique thing about this building, you see this flex duct. This was from a kitchen vent on the middle floor that came up through the attic and then was vented down. Both the front and back of this building had vaulted ceilings, framed with 2x10 joists, and then the center section is the attic space, the vented attic space we're in this photo. So that was one unique detail. And then we're looking at a fireplace chimney, and that fireplace is actually down in the basement, and when we pull back that cardboard ice dam, you could see all the way down to the basement floor. So another large bypass coming up and bringing heated air up into the attic. Plumbing chases. This was another problem where the party walls between the units, partition walls, there are walls that are sheetrocked on both sides for fire code reasons, and it's open from the heated basement floor all the way up to the roof decking. And the temperature in there was also similar in temperature to the temperature in the room, more indoors than outdoors. And so even if we did a perfect job of sealing all of the bypasses in the units, if we didn't deal with this detail, then we would have problems with air getting up into the melting snow on the roof at this location. And this is about 6 inches wide. So you'd have a strip 6 inches wide where it's melting snow. So that would need to be dealt with also. Additional bypasses. This is looking down the 2x10, 2x12 joist space. Some locations they had blocking with holes drilled in. If those holes were open to the soffit, we'd feel below zero air coming up through there, and we certainly didn't. There wasn't much movement, if any, coming from the low soffit venting. So again, it has ridge venting, but that's just venting the air that's leaking from the house out through the attic. If you have low attic venting, it's going to draw up cold air from the outdoors and help keep that attic. Ideally, you'd like the attic space to be the same temperature and relative humidity as the outdoors, so you don't have those kinds of heat loss durability issues that you have in cases where that's not happening. This is another vent like that one we saw in the other photo, only this is going down the front of the house. This is the 2 bathrooms from the upper floor that are being vented out through, again, down that vaulted area. So this is a flex duct that's running all the way down and venting out through the soffit. What we ended up doing to get some low venting to this attic space without having to tear everything apart was we revented these bath fans up through the roof and used these ducts going to the soffit as our air intakes. So now we've got one going down the back, one going up, coming up from the front, one coming up from the back, bringing cold air from the outdoors up into the attic space to help keep the space close to temperature and relative humidity of the outdoors. And once we disconnected this duct, you could feel really cold air from the outside being drawn up into this space. So it was very effective at getting airflow up into this attic space to help align those pressure and thermal boundaries. Just a little bit of the damage that was occurring there. You can see not only the beautiful view here, but you can see the houses in the background here were not part of this complex, apparently built by a different builder, and did not have the icicle and snow ice dam problems that this building had. So if builders, you would think builders that are building in this climate would be able to would have this figured out. But just to show that you can build even in these extreme climates and not have these problems if you're paying attention to the attic air sealing, attic ventilation issues. So when do we use direct zone pressure diagnostics? When does it make sense to use it? If we have a primary zone where a hole can be added for advanced zone pressure diagnostics, we'll call this a primary zone. So any zone where a hole can be added for pressure diagnostics we'll refer to as a primary zone. Secondary zone is where a hole can't be added, but it's a zone that has a large volume or is connected to a space with a large volume. An example of that might be stud cavities that are open into that we suspect are open into a drop soffit, which we suspect is open into an attic space. Then might make sense to do some direct zone pressure diagnostics. And by direct, again, I mean simply taking a pressure measurement in that zone to determine if it's more indoors or if it's more outdoors. So these are the zones where it makes sense to take those direct measurements. If the zone has is likely to have a large thermal or air leakage connection to the outside, such as chaseway, could be a plumbing chase, a large plumbing chase, or a chimney chase primarily. Chimney chase like, or a duct chase. So that may be open on the top. A large chase that may be open on the top and have a large thermal or air leakage connection to the outdoors through the attic space. Non-applicable zones or zones not appropriate for using zone pressure diagnostics. If we have a single wall or floor cavity that's not likely connected to other multiple cavities, it doesn't make much sense to take direct zone measurements in those locations. And some applications that aren't appropriate uses of zone pressure diagnostics, using pressure pans to determine if recessed lights are leaky, or measuring bedroom pressures with the house at 50. And after we go through a little further explanation of interpreting these numbers, we'll come back and talk about these 2 or 3 issues later. These are some zone pressure charts that Michael Blasnick and Jim Fitzgerald came up with, and it shows the leakage ratios, the ratio of zone pressures to the relative size of leaks. So on the charts on the left side here, we're talking about zone to house pressures and zone to outside pressures with the house at 50 pascals. Let's start out with the 25 number, where the zone to house and zone to outside pressures are both at 25. So the house is at 50. You stick a probe into an attic. You're measuring zone to house pressure, and you're getting 25 pascals. Or if you're measuring the attic pressure with reference to outside, then you're getting 25 pascals. So those numbers are equal. On the right, it's showing that when you have instances like that the house to zone leakage and the zone to outside leakage are the same. So the size of the leak between the house and the attic are the same as the size of the leak from the attic to the outside. In other words, the bypass leakage is the same as the roof vent leakage, the amount of leakage going through those 2 zones. Or if you want to look at it as the size of the hole between the house and the attic is the same size, the size of the hole is the zone of the outside. If we move down to 48, if we've got 48 zone to house or 2 zone to outside, we've got a 1 to 8 leakage ratio. So the bypass is 1/8 the size of the roof fence. In other words, if it's an attic zone. So now we're getting better. Our attic is closer to outside. Now we've got a much better thermal boundary and pressure boundary alignment. Ideally, we'd like to be more in this 1 to 13 ratio, 49 to 1, where our attic is much more outside. But somewhere in the 1 to 2 is really where we want to go. But one thing to keep in mind is that this shows a couple of examples where we could have an attic zonal reading of 25 pascals. That means that the hole between the house and the zone is the same size as the hole between the zone to the outside. It doesn't tell you anything about the size of the hole. It just tells you that the size of the hole is equal. So in that example I used, we could, in theory, even though we had all of those horrible bypasses we showed in the attic, we could add enough venting to make to get the zonal pressure numbers better. but by adding more leaks, you make your blower door numbers go up, and you make your energy costs go up. So in this example now, we're showing that we've got a zonal reading house to zone of 48. So now our hole between the house and zone is 1/8 the size of the zoned outside hole. Again, it doesn't tell you anything about the size of the hole, just the ratio of leaks. So you can see in this example, the hole size, we've got a 48 Pascal reading house to zone. We've got to bypass this size. In our previous example, we had a 25 reading and we had a hole the same size. So it's possible to have the same amount of bypasses with a reading of 25 as it is with 48. So this is important, very important, probably the most important thing I want to stress today is that the reading you get house to zone doesn't tell you anything about the size of the hole. It tells you about the leakage ratio, house to zone and zoned outside. So now that we've had a little further explanation of what zone pressure diagnostic numbers mean, you can see that if you're measuring a single wall cavity or a single floor cavity, that's not likely connected to the outside. It doesn't tell you very much information. For example, if you've got an outlet on an exterior wall or an interior wall that's not likely connected to other zones, and you stick a probe into that cavity, what that's telling you is the ratio of leakage between the house and that cavity and the outside. And that's not very useful information. It's not telling you anything about how much leakage there is. It's just telling you about that leakage ratio. Not appropriate applications of zone pressure diagnostics: using pressure pans to determine if recessed lights are leaky. When you're using a pressure pan for zone pressure diagnostics, you're creating an additional zone, and that zone is the zone inside the pressure pan. And you're pushing that pressure pan against the wall cavity or ceiling cavity in this instance if you're measuring a recessed light. And if the pressure pan, the gasket on the pressure pan is making a perfect seal, then if you have even a pencil or pinhole, if you have even a pinhole of leakage between the pressure pan space and the attic, what you're going to be reading is the attic pressure. So, if you do a pressure pan reading and determine the recessed light is leaky and then seal up the recessed light and do a pressure pan reading again, you may likely get the same number, whether you did an almost perfect job of sealing it or not, because you're essentially, if that pressure pan is fitting perfectly tight, you're reading the pressure between that pressure pan and in the attic space. You're reading that pressure, or the pressure inside the recessed light cavity. So, and then think about now with that understanding of what these zone pressure diagnostic measurements mean. Think about measuring bedroom pressures with the door between the bedroom and the main body of the house closed, and with the house at 50 pascals. So you have the blower door cruising 50. You close the bedroom door. You measure the pressure under the door, and you wait for the house to stabilize at 50 pascals and take that reading. What that's telling you is the ratio of leakage between the house and that bedroom as compared to the bedroom to the outside. It's not telling you anything about the size of the hole from that bedroom to the outside. It's just telling you about that leakage ratio. A little more about attic venting. Again, what was mentioned before was that low venting is important. Otherwise, if you only have high venting, if you only have a ridge vent or high roof vents and no low roof vents, then you're just venting out air that's leaking into the attic space. That's where it's getting its intake. If you have enough low soffit venting and ventilation chutes between the soffit and the attic to allow airflow above the insulation to get into the attic space, then those the air is going to be vented out through the top, and it's going to draw air in through those low roof vents. And air is going to go through the path of least resistance. So it rather than pulling it through small cracks and into insulation, it's going to be more apt to pull that air from the outdoors through those wide open soffit vents. So in order to keep the attic at similar temperature and relative humidity levels to the outside to help prevent these ice dam issues and durability issues in attic spaces, it's important to have both high and low venting if you want to keep the attic space at close to the same temperature and relative humidity as outdoors. Adding attic venting can improve zone pressure diagnostic numbers. It will also make attic spaces colder during the heating season and can lead to a whole other set of issues. If you don't seal bypasses and you add additional venting to an attic space, you can be causing problems that weren't there before. Sometimes there'll be visible signs that there's been ongoing issues. So even if you don't have extreme temperature conditions, you can see by the discoloration of roof sheathing or active mold growth that there's been problems up there. Other times there'll be drips on top of the insulation if frost has been melting, and people can get pretty creative at trying to catch roof leaks and water drips. So we want our pressure boundaries and thermal boundaries to line up, and we can tell if they are by the pressure numbers we're reading. We want our conditioned spaces to be outside, close to temperature and relative humidity is outdoors. We want to make that boundary as tight as possible. That's the goal here. We want to make that boundary as tight as possible so the insulation we have is effective, so the air isn't getting right past the insulation and causing problems. And anytime you add roof venting, you're going to increase your blower door number and increase your roof venting becomes less of an issue as you make the boundary tighter and tighter. You don't need as much attic venting to get those pressure boundaries and thermal boundaries to line up. Whenever you have high interior humidity levels, and I would consider that over 40% during the heating season, it requires perfect air sealing. Otherwise, you're going to have these attic condensation issues and durability issues. Small volume attics require better air sealing details because the temperature and relative humidity levels can rise easily because of that small volume. So next we'll talk about what is advanced zone pressure diagnostics. It requires using software or charts to calculate the CFM leakage between the house and zone. And it requires adding a hole or opening a door, house to zone or zone to outside, to make those calculations. When we're using advanced zone pressure diagnostics, first we'll record the baseline adjusted house to zone and zone to outside and CFM 50 of the house. When we're doing a CFM 50, we're changing the pressure in the house by 50 pascals from what the baseline was. So we're increasing the house by 50 pascals. And when we're measuring house to zone, zone to outside pressure numbers, we want to be measuring the change in pressure caused by the blower door. So we'll need to know what the baseline readings were. And that becomes especially critical as we start getting closer to zero between the attic and outside. The baseline becomes more critical. Next step is we'll open a door or add a hole. house to zone or zoned outside and return the house to 50 pascals. If we don't have the ability to add a whole house to zone or zoned outside, it's possible to temporarily seal off some roof vents and take the reading and then unseal the roof vents. So by unsealing the roof vents, we're essentially adding a whole attic outside and returning the house to 50 pascals, and we can use that to get our measurements also. And then we'll record the new house to zone and the new zone to outside and the CFM 50 of the house. And then we'll need to use software charts to calculate the leakage areas. So if we have examples where there's extreme problems with either attic moisture or high humidity levels in crawl spaces, moldy crawl spaces that are getting into houses, or indoor air quality issues in the garage, such as carbon monoxide, or we store gasoline out there, pesticides, herbicides. We don't want all of those chemicals getting into the house. It becomes more critical to use those advanced zone pressure diagnostic methods. So quickly, I'm not going to spend a lot of time on this, but the math behind the measurements. What was figured out to calculate these leakage ratios is if you have 4 equations and 3 variables, you can solve those equations. So the 4 formulas that were used to come up with these measurements when they developed the charts and the software is the leakage through the blower door is equal to the attic bypass leakage plus all the other leakage is the first equation. Second one is leakage into the attic is equal to leakage into the house. And the other 2 formulas, once the whole is added, and that's why the whole needs to be added, is to get those additional formulas to solve for the missing variables. The air going out of the house is equal to the bypass leakage plus the added whole leakage plus all the other leakage. And then the fourth, air leaking into the attic is equal to bypass leakage plus the whole leakage. So those of you engineering types who want to do the math longhand, you can. The rest of us will use charts or software to calculate those numbers. To identify how big the holes are in the pressure boundary is why we use the zone pressure diagnostics, and to see how much CFM reduction we can expect by sealing those holes in the pressure boundary. So if we have extreme cases where we want to document what's causing these ice dam problems, attic moisture problems, air quality problems, we can take these measurements and determine how much leakage there is from that moldy crawl space into the house. We can seal up those bypasses, those air leaks, and then test again to make sure we got all of those. And when it's important to document that for air quality or durability or damage issues, it's good to do that. So even if you're not doing it on every house, it's good to practice it, and especially after this training, it makes sense to start practicing it and not necessarily doing it on every house, but at least are familiar, so when you do need it, you'll have the ability to do it. So the expected value of doing zone pressure diagnostics must be greater than the cost of performing the test. And if you have a pretty straightforward rambler where all of the bypasses are accessible, it probably doesn't make a lot of sense to be doing the advanced zone pressure diagnostics testing. If you have complex houses where it's difficult to determine where the pressure boundaries are, it makes sense to calculate how much leakage there is between the house and that zone. If you have indoor air quality issues like we talked about with the garage or moldy crawl space, then it would make sense to do the zone pressure diagnostics, especially extreme examples. And durability issues for sure, if there's warm moist air leaking into a cold attic causing problems. So there's a few different ways of calculating the advanced zone pressure diagnostics. You can use the ZPD calculation utility software that's free from the Conservatory.com website. You can use the Olson Cox charts that we'll be referring to in this presentation. They're available at the CARG.com website. We'll also make these available to everyone who attended this webinar, and we'll be making them available through our website in the near future. And then there's a Zip Test Pro 3 for Texas Instruments, the TI-89 titanium calculators, available at the CARG website also, and that's similar software to the ZPD calculation utility, but if you don't have a computer in the field, it allows you to, if you have this calculator in the field, to do those calculations. Energy Conservatory website, if you go to products and then software, scroll down towards the bottom of the page, you'll see that zone pressure diagnostic calculation utility. And then there's charts we'll be going over that you can use in the field too. And you'll need to open the door between the house and the garage or garage to outside. This is a pretty easy test to do, as you'll see. And you'll open the door that has the highest pressure across it. So and most of the time that will be the door between the house and the garage is the door you'll open. But you might run across some townhomes where it's fairly tight garage where you'll need to open the garage to outside test, because that will have the highest pressure across it. Attics, opening an attic hatch can be more tricky. You want to make sure you're not going to be pulling insulation from the attic into the house with the blower door running. You can pressurize the house to do that test if you're concerned about that. And these numbers work either depressurization or pressurization. This is what the chart looks like for opening a door. And most typically that's done in a garage space, but could be done in an attic space if you got a door going up to an attic. And there's one chart for opening a door between the door and between the garage and the house, and there's another chart for opening the door between the garage and the outside. And we'll go over these in a little bit more detail. So when we're using the attic chart for adding a hole, and I'll show an example of this also. You'll depressurize the house to 50 pascals. You'll measure the CFM 50 and the zonal pressures. You'll make a hole in one of the barriers. You'll adjust the fan to keep it at 50 pascals and measure the new CFM 50 and the new zonal pressures, and then use the chart to get the total path or the amount of CFM reduction available through those charts. This is just to show you some one way of taking those attic pressure measurements. First, we'll take our CFM 50. We got it set to in the pressure flow at 50 mode. We get close to 50, and we take our CFM 50 number and record that. And these are baseline adjusted numbers. And then in this case, we're measuring attic to outside. So, and we're in the pressure mode. So after you recorded your CFM 50 number, you can simply turn the gauge off and turn it back on again, and you'll be in that default pressure mode, PR mode. And that's what we're in this case. So now we've got our blower door sealed. We've got the rings back on the blower door. We're in the pressure mode. We've used that splitter that came with your DG700 gauge, the T connection with the two short pieces of hose, and we've connected that on the reference tabs on channel A and channel B. So we've got our hose to the outside connected to both channel A and channel B. If you don't have one of those T's, you can run a second hose to the outdoors. So the key here is you want, if you're measuring attic to outside, and you want to look at your house pressure and your attic pressure. So we're recording baseline numbers here, and you can see on the channel A we've got a -1 pressure from the housed outside, and on channel B we've got -2.9 from the attic. We've got a blue hose going from the attic, and that's our attic to outside baseline number. And there's a lot of things that can affect attic pressure numbers. Temperature attic to outside is one of them. Temperature house to attic is another. Wind can have a big effect on attic pressure numbers. So the attic to outside baseline isn't necessarily the same or even similar to the house to outside baseline. Then you'll bring the house to 50, and remember again, we want the house to change by 50. So our initially we were at 1 Pascal. So now we're bringing it up to about 51, close to 51 pascals. On windy days, it's going to be hard to hit it exactly. So we've changed our house pressure from 1 to 50.1, so we've changed it by about 50. And now our attic is at -22.2. Baseline was about 3, so we've changed it from about 3 to about 22. So we've changed it by about 19 pascal. So our attic pressure number in this case is about 19 pascals. And it can be tricky to get a probe up into an attic. There are a lot of different type probes you can use. There's it's showing a thin copper tube here. The inside diameter of the hose is about 1/8 inch. So you want to get something either exactly 1/8 inch or a little bit smaller than 1/8 or a little bit bigger than 1/8 will work fine too, as long as it fits snug in the hose. A lot of people have been using brake line tubing, metal brake line tubing, because it's flexible. It's easier to make sharp turns and bends with it to get around attic hatch trim, or the sheetrock lip around an attic hatch, so you can bend it and get up into a corner of an attic hatch that way. You can close doors on these kinds of tubes. It's a good idea to also add an extra tube that you can throw up into the attic farther. So if you're doing the advanced zone pressure diagnostics where you're removing the attic hatch, you want that hose up farther into the attic, where it's not in an area of air movement, so you have a more stable pressure. Brake line tubes come in 2 diameters. One is a little bit bigger than 1/8 inch. One is a little bit smaller. Either one works fine. The smaller one is easier to bend and make sharp turns with, to get under doors, or bend to get around tight angles. So now we'll do a demo of using some simulation software. This is some software that was developed by Colin Olson in our office. He did a presentation with Anthony Cox at the Wisconsin Better Buildings Conference, and that's where most of this PowerPoint I'm using came from. it was shortened up to fit into this time frame, and then that case study was added to it. But that was the origin of this PowerPoint presentation. So what this simulation software is it has 3 zones. It's got the house zone, it's got an attic zone, and it has a garage zone. As you can see, we've got a pressure gauge in here. We've got a blower door set up here. And we're displaying the blower door flow. So this is our flow through the blower door. We're set to cruise 50 pascals, and we're depressurizing. It's showing on the left channel here, it's showing the house with referenced outsides. We've got our green hose going outdoors, and then our other hose is measuring the attic to house pressure measurement. So we can click on where we want this to take measurements. So this the gauge is displaying the attic zone to house pressure, and that's showing at 42. And it's also displaying what the attic to outside number is. So we're not taking that measurement with this gauge, but it's showing that pressure measurement. And you'll notice that the 42 plus 8 equals 50 because our house is at 50. So the attic to outside plus the house to attic is going to equal 50. If we move this over to the garage, you'll see that now it's measuring 45 to the garage, and it's displaying 5 pascals garage to outside. You also notice that the each zone has a hole to the outside, and each zone has a hole between the other 2 zones. So you can see all of the holes. These holes are adjustable. One other thing you'll notice is that the house is blue, the attic is a shade of blue, the outdoors is white, and the color will change as the pressure becomes closer to that zone. In other words, I can change the size of the hole. You can see as I'm making this hole smaller, the attic becomes more like the house, so the color changes, so it's more like the house. As I make that attic venting bigger, the attic gets more like the outside, and it gets closer to that white color of the outside. What you'll also notice is as I make those vents in the attic bigger, our blower door number will go up. So now we're at 3595. As I make these, as I make the holes bigger, our blower door number goes up. So adding roof venting changes the amount of air that can flow from the attic to the outside. Because and same with if I make the bypasses smaller, obviously our blower door numbers will go down. As I make the bypass bigger, our blower door numbers go up. That one's we all understand that concept. So let's do a couple of zone pressure diagnostic tests. We'll do the garage test first, and then we'll enter that information in the charts. So first, there's 3 numbers we'll need to record. We'll need to record the CFM 50 of the house before we add the hole, the CFM 50 number after the door is opened. So blower door number before the door is open, blower door number after the door is open, and the pressure between the house in the zone or the zone to outside before the door is open. Those are the 3 numbers we'll need. So we've got 3595 for our blower door number initially. We've got 45 from our house to zone, 5 from our zone to outside. And once we open the door, click on this box to open the door. Now our garage becomes part of our house and is at the same pressure. And our new blower door number is 4503. So those are the numbers we'll need to do the the Advanced Zone Pressure Diagnostic number to calculate the flow between the house and the garage with the house at 50. Next, in order to do the zone pressure diagnostics with the attic, we'll need the before, adding the whole blower door number. We'll need the after blower door number. We'll need the attic pressure before we add the hole and the attic pressure after we add the hole. So we've got 3595. We've got a zone to house number of 42. We've got an attic to outside number of -8. And then we open up that attic hatch, and this attic hatch is we'll say is about 20 by 30, so 600 square inches. And with these charts, they're using what's called a hybrid method to do the calculations where you don't need to add the size of the hole into the software. So we need the size of the hole for this to do that calculation that we're looking for, but we don't need to add that in the chart. We don't need the size of that hatch information for it to be able to do that calculation. So now we've opened that attic hatch, and now we can see our attic is more like our house pressure because we've added a large hole. Our new attic to house reading is 13.3. Our new attic to outside 36.7, and our new blower door flow 5360. So now we'll enter that information from those two examples in the charts. All right, and this is our attic, or our chart for opening a door. And we're opening a door from the garage to the house because that had the largest pressure across it. That had a pressure of 45. Now with these charts, like I mentioned, there's 3 numbers we need to add. And then this example I'm using is an Excel spreadsheet, and we'll make this available as well as making the charts available. And I would recommend getting familiar, and we'll make that zone pressure diagnostic simulator available too, so you can play around with making holes bigger or smaller, and practice using these charts using the spreadsheet. I recommend starting that way because it's doing all the calculations for you when you add those. And then as you get more familiar with using the charts, you'll be able to use these charts in the field without a computer, but you will need a calculator to do the calculation. So what we're entering in here, these charts look a lot more complicated than they are. They can be intimidating at first, but once you get familiar with the process, it becomes pretty simple eventually. So here's the numbers we'll enter in. The house with respect to garage number was 45. The CFM with the door closed, 3595. The CFM with the door open. So these numbers in red are the numbers we enter in. So with the door open, we're at 4503. So what it's calculating in this cell is the difference between these two numbers. So the CFM door open minus the CFM door closed gives you, in this case, 908. Those 908 numbers are carried down here automatically by the spreadsheet. When you're doing it in the field, you'll need to carry those numbers down there. And then we'll look for these multipliers. And to find the multipliers, we use this chart. So we're at 45, so we simply go to 45 here, and it has the multiplier, our multiplier interior, exterior, and path, interior, exterior, path, and then it multiplies them across. It comes up with CFM, so now we know our CFM leakage from the garage to the house. 280, or about 28 square inches. Our CFM garaged outside at 50 pascals. The garage isn't seeing 50 pascals, so this amount of air isn't moving. It's only seeing 5, so the amount of air movement is smaller. But CFM 50 garaged outside is 1170 or 117 square inches. So the CFM reduction possible is about 262. So that's the using the garage chart. And next we'll use the house chart here. And with this one we had 4 numbers we need to enter in. So the numbers in red here again are the numbers that we need to enter in. Our CFM before adding the whole, our house to zone before adding the whole, our CFM 50 after adding the whole, our attic pressure number after adding the whole, and then in the spreadsheet again it calculates the difference between CFM before, CFM after, and then our multiplier to figure out our maximum reduction. And to get this multiplier number, we'll look at numbers going down this way are our starting pressures. Numbers going across are pressures after adding the whole. We started out at 42, and we move across to our pressure after adding the whole, which is 13, and we come up with a multiplier of 0.6. So this is telling us our maximum reduction possible is 1064. So our blower door number was starting out at about 3,600, and we can reduce it by over 1,000 if we seal those leaks between the house and the attic. So pretty significant. The colors on this chart are important also. We'd like to be in the gold zone here because gold, it's showing the uncertainty levels associated with those colors. With gold, we've got about a 10% uncertainty in those numbers. Once we move out to the purple, we're in the 15%. The beige is 20, and the darker blue is 25. Out in the white, we're at greater than 26%, and it's probably not worth going through the trouble of taking these numbers if we're out in that white zone because the amount of uncertainty is so high. If we're bothering to take the numbers, we'd like to get the best numbers we can, and those numbers would be in this gold zone. The numbers that we took during this example, we were starting out at 42, we moved across to 13, we were out in this purple zone. The only way we could get to the gold zone when we're starting out at, we can't get into the gold zone when we're starting out at 42 because it's we can't move over far enough. So in order to get in the gold zone, our starting pressure needs to be somewhere between 25 and 40. So how are we going to, in this case, get into that zone? One way of doing it, we could temporarily seal off some of the roof vents. And in this example, if we sealed off, the amount of roof vents is equivalent to about 6 roof vents. If we sealed off 2 of them, then that would move our number down farther along here, and then when we added the whole, it would have a bigger effect because now that attic is tighter, and that would move us over into this gold zone. So there are a few tricks that you can do to get your pressure number measurements to become more accurate. If you need finer definition on how much leakage there is a way to do that. And then over towards the bottom corner of this chart, it shows you based on your uncertainty what the range is. So in this case, it's showing that our maximum reduction is about 1064. We've got a 15% uncertainty. So really what that's telling us is we're somewhere between 900 and about 1225 CFM is our potential. So that's about what our uncertainty is, plus or minus 15%. in this example. So that gives you kind of an overview of the charts, and as I mentioned before, playing around with the simulator and with the spreadsheet will help you get a little bit more familiar with achieving these numbers. And after you're comfortable with that, then try using the charts in the field. You'll be able to better understand where those multipliers come from and how to do the calculations once you get the 4 numbers in red entered into the software. All right, then we'll go back to our PowerPoint here. All right, so there's the chart we saw, and we'll make these charts available. Some additional information that's available. There was a study done back in the mid-90s. Gary Nelson, Colin Olson with the Energy Conservatory were involved with that. Also Dave Bohack, Jim Fitzgerald with Center for Energy and Environment, and the Wisconsin weatherization crews. And they did some extensive testing on using zone pressure diagnostics in weatherization. And it's a pretty technical study, but it has a lot of really interesting information in it. And that's available at the Energy Center of Wisconsin's website. And the connection is there. And this PowerPoint will be made available on our website, so you can track down this additional information. Some of the references that were used were a couple of articles on zone pressure diagnostics that were in the Home Energy magazine, May, June 2002, and also September, October 1994. And both of those are available at the homeenergy.org website. Thanks for attending our webinar. If you have any additional questions, feel free to email or call. All participants will be receiving an email notice when the recorded presentation will be available, and when the and our slides will be available on our website in PDF. And there's also that Excel spreadsheet, the ZPD trainer, will be made available for you also. Thank you.